Hi, welcome to Chemical Bonding Part 2. My name is Dr. English. Today we're going to be talking about an introduction to ionic bonding. Specifically, we're going to be looking at what is ionic bonding, electrostatic forces, visualizing ionic bonds, and a little bit of practice at the end. One method to achieve a complete octet is to transfer electrons, where metals are going to donate electrons to become positively charged ions, and nonmetals will accept those electrons to become negatively charged ions. Note, the number of electrons lost must equal the number of electrons gained. This is known as the conservation of charge. And if we look at our little example down here, we see the sodium donating an electron to the chlorine. They come together and they form a much more stable chloride ion. So again, sodium donates an electron, this accepts it, positive, negative, comes together to be more stable, energy is released. In the formation of a chemical bond, one must be able to account for all electrons lost and gained. The ionic bond is the positive, negative electrical force of attraction between the ions. These are known as electrostatic forces, the force between the particles that are caused by their electric charges. So if we look at our little example here, we see the sodium again donating the electron to the fluorine. The fluorine, it accepts it, the sodium becomes positive, and the fluorine becomes negative, forming that ionic bond between the two ions. So we go from atoms to ions, this becomes positive, this becomes negative, we form that ionic bond. Let's look at a sodium chloride example. The sodium atom, which is a metal with an electron configuration of 281, gives up its one valence electron in the third shell to become a sodium ion with a configuration of 2-8. In other words, we're losing this one valence electron right here. The sodium ion has a noble gas configuration 2-8 like neon. The chlorine atom, a nonmetal with an electron configuration of 287, will accept the valence electron from the sodium into its third shell to become a chlorine ion with a configuration of 288. The chloride ion has a noble gas configuration like argon. So as we can see, in both of these situations, the sodium atom is going to become an ion by giving up its one valence electron. The chlorine atom is going to become a chlorine ion by gaining that one electron. Let's talk about how we can visualize ionic bonds. One can represent the ionic bond using dot structures. Here I have the Lewis dot diagram of sodium with its one valence electron, giving it to this chlorine atom right here. When this sodium atom loses its one valence electron, it's going to become a sodium ion with brackets and a +1 charge. Notice there are no other dots around this symbol. That's because when we do Lewis dot diagrams, we only represent the valence electrons that are involved in bonding. On the flip side, here we have the symbol for chlorine. It has its 8 valence electrons with a charge of -1 on the outside. This is showing that electrostatic force of attraction between the sodium ion and the chloride ion. We can also represent the ionic bond using Bohr models. So as you can see over here, this Bohr model of sodium donates its one electron from the outermost shell to the chlorine atom right here. As a result, the atomic radius of the sodium decreases while the radius of the chloride ion increases as it gains that one electron. Now let's do some practice. For each of the following examples, identify the metal and the nonmetal, draw the appropriate dot structure for an atom of each of the two elements, use an arrow, show the transfer of the electron from the metal to the nonmetal, and then finally write the dot structure for the ionic bond. So let's do one example together. Here I have two elements, K and F. K represents potassium and F represents fluorine. If we look at these two, we can say, well, the metal must be potassium from where it's located on the periodic table. And we know that fluorine is most definitely a nonmetal. So the first thing that we're going to do is represent the Lewis dot diagram of each of these. So I'm going to draw the symbol for K, and it has 1 valence electron. Then I'm going to draw the symbol for fluorine, and it has 7 valence electrons. So I'm going to represent those as little x's, 2 on each side that represents those valence electrons. Then it says use an arrow, show the transfer of the electron from the metal to the nonmetal. So here I'm going to circle the valence electron from the potassium and show it donating to this fluorine atom over here. As a result, I can now write the dot structure for the ionic bond. So now I'm going to write K with brackets around it, plus 1, because it lost that 1 valence electron. I'm going to write my fluorine with its original 7 valence electrons, 4, 5, 6, 7. I'm going to represent the electron coming from the potassium as something different, just to show that it came from the potassium atom. We now have a fluoride ion, so I'm going to put brackets around that, with a -1 charge. This now shows the electrostatic force of attraction between the potassium ion and the fluoride ion, showing the ionic bond. Now what I'd like you to do is stop, look at the 2 elements and the 2 examples given to you, see if you can follow the procedure from the example given, and write the ionic bond. Welcome back. Let's see how you did. So the first thing that you needed to do was look at the 2 elements and identify the metal and the nonmetal. You should have identified the magnesium as the metal and the sulfur as the nonmetal. When you did the Lewis dot diagrams, magnesium has 2 valence electrons, sulfur has 6 valence electrons. So these 2 sides right here have their maximum of 2 electrons. So one of magnesium's valence electrons could have gone to this location, the other one over here. As a result, we have a magnesium ion with a charge of +2 and a sulfur ion with a charge of -2, because we can see where it gained its 2 valence electrons to get its full octet. Let's look at our next example, which was a little bit tricky. Calcium is our metal, chlorine is our nonmetal. Calcium has 2 valence electrons, chlorine has 7. So now we're in a situation. Calcium must give up both of its valence electrons. It just can't choose and say, hey, I just feel like giving up one of my valence electrons today. So as a result, and you can do this, you bring in 2 chlorine atoms. So one of the valence electrons from calcium goes to one chlorine, the other valence electron goes to the other chlorine. As a result, there's 2 different ways that you could represent this ionic bond. You could do the symbol for calcium. Remember, no more electrons around that calcium. It lost its 2 valence electrons. Do not put core electrons in. So the calcium symbol, brackets with a charge of +2. And then you could have a coefficient, a big 2, in front of the bracket saying, hey, I now have 2 chlorine ions. So the chlorine with its original 7 valence electrons, the 1 electron that it gained from the calcium with an overall charge of -1, but there are 2 of them here. The other way, if you feel more comfortable, that you could represent it is, again, your calcium symbol, the brackets, the +2 charge, and 2 written out examples of the chlorine ions. So each chlorine here has its original 7. We're seeing the electrons that were gained overall to give us our charge of -1. Either one of these is totally acceptable. So what did you learn? We went over what is ionic bonding, we talked about electrostatic forces, we did some visualizing of ionic bonds, and finally we did a little practice at the end. Need more help? Feel free to contact me. Have a great day.